Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And this is part 6 of a little mini-series that I'm doing within that playlist. This mini-series deals with randomized complete block designs. And what we do is we're going to cover in R what we did in the first 5 parts. So if you haven't watched the first 5 parts of this little mini-series, some of what we do may not make sense. So first, I searched the internet for data for a randomized complete block design. And I found some data from Montana University where they were looking at the strength of cotton based upon how much potash fertilizer you used when you planted the cotton. Now they treated the plots of land like blocks. And then within each block, they plotted the different amounts of potash. So let's load the data here into, I call it Montana because that's where the data came from. And they have it sorted in an order that I don't want. I want it by treatment and then block. So potash by block, and then I print it out so you can see. So potash is ordered first, and then block 1, 2, 3, 1, 2, 3, and then strength is the strength of the cotton based upon. So that's the response variable. Now I want to make each of the potash and block variables factors, so that's what I do. And plus it helps in this strip plot that I do. So this is the amount of potash, and then it's plotted by block. Notice that 54 tends to be the highest, the highest strength, cotton strength. So let's plot it by block. So this is a block is a plot of land. And notice red is the second level, black is the first level. And so it tends to be the highest. Now, in part 1, in model development, we created, the response vector. So I'll put it in Y here. Let me make these plots go away. So here's our data. And remember, it's sorted by treatment and then within block. And if we look at the cross tabs, this is the data just presented again. And then the row means and column means if you want those. And there's the grand mean. So we need B and A. B is the number of blocks and A is the number of treatments. So it's 3 and 5. And then from that, since we know the order that it's sorted by, treatment and then blocks, we can generically create this design matrix. So the first column is all ones. Then the next 5 columns deal with treatments, right? And then the next 3 columns deal with the blocks. And this is like the little identity matrix going down the rows. So let's create little column spaces. So the first column we'll call 1 because it's always a vector of 1s. X tau is the portion of the design matrix dealing with the treatments. X beta is the portion dealing with the, the blocks. Now in part 2, we started looking at perpendicular projection matrices onto these different column spaces of the design matrix. So we need the library mass because that in there has a generalized inverse function, and it allows us to create the least squares estimate for the beta parameter. And so this is mu, tau 1, tau 2, tau 3, tau 4, tau 5, beta 1, or block 1, block 2, block 3, or beta 1, 2, 3. Now, one thing to remember, the least squares estimate is not unique. There's an infinite number of possibilities there. And actually, this is a topic, I hope I don't talk too much about it, but that's what estimability deals with, right? There's an infinite number of beta estimates, but we can take certain combinations of these betas and end up with a unique estimate. And that's the whole concept of estimability. Okay, but we'll get to that. So then to create a perpendicular projection matrix, we take the vector times transpose vector. So for instance, x transpose x inverse x transpose. But with J, there's just one column. And then m tau is the perpendicular projection matrix onto the column space of x tau. M beta is the perpendicular projection matrix onto the column space of x beta. M is the perpendicular projection matrix onto the whole design matrix, so the column space of x. I BA, so that is the identity matrix of dimensions, A times B. Now, to show some of these properties, perpendicular projection matrices should be symmetric. So what the next three lines do is I take the transpose and compare it with the untransposed, and they are equal. Now they're idempotent, so I multiply it times itself and then compare it with the original. And if you notice, all of these are true because they're all perpendicular projection matrices. Now this last one, we found the format of M, the perpendicular projection matrix from column space of X, and it ends up being M tau plus M beta minus J. And to show that they are equal, we compare them, M versus that M tau plus M beta minus J, and they are all equal. Now, more properties. If we create what's called the treatment mean vector, we take M tau times Y, and to show you that it's the correct, I just calculate the means by potash. Now look at this, 785, and it's repeated B times or 3 times, 8.0533, 74, So that's the format of the treatment mean vector. Now the block mean vector is M beta times Y. And notice that it's repeated. So it takes mean block 1, mean block 2, mean block 3, and just puts them at the first 3. And then it repeats A times, so 5 times. So that's the structure of the block mean vector. The grand mean vector is just a constant vector with the grand mean, so 7.722. Now, one little note on the website from Montana University, they have a 3 there, so that's 7.723. I've double checked all the data and I've double checked everything, and I actually think it's a typo on their part, but I'll let you guys decide that. Now the degrees of freedom is actually the rank of the matrix when it's in quadratic form. So the degrees of freedom treatment is the rank of M tau minus J. But since they're perpendicular projection matrices, they're idempotent. And since it's idempotent, it's just the sum of the diagonal elements, which is A minus 1. So it's 4. Same way with the degrees of freedom for blocks. It's the rank of M beta minus J, which is 2, right? B minus 1. Degrees of freedom for air is A minus 1 times B minus 1, which is 8. You can see that 4 times 2 is 8. Now partitioning the sums of squares, this is the total, I minus J in quadratic form. Y transpose I minus J, Y. And if we look at that, so we got 1.179, and here's the ANOVA table for it. And it doesn't put total, but if you were to add these 3, it would equal 117. So that's what I do in this next step. I just grab that table and sum that column, and it does equal the total sum of squares that I got before. Now the treatment sum of squares is Y transpose M tau minus J Y, and notice that 0.73244 equals the sum of squares for treatment, which is potash. The block is the same, 0.0971. The sum of squares air is the same, 3495. And notice that so this one I use Y transpose I minus M Y. But here I put in what M is, which is M tau plus M beta minus J. And if we run that, we should get the same thing, and we do. Now the F test, and what I do is I reprint the ANOVA table because it's kind of going off the screen. So we calculate the mean square for treatment, which is 1831.1, which is the same as we get here. Now the mean squared for block is 0.04, which is what is in that ANOVA table. Mean squared of error. And so to get these mean squares, you take the sum of squares divided by its degrees of freedom. And then these F values are the mean square divided by the residuals. Mean square divided by the residuals. So that's what this next step does. So 419 is for treatment and 1.11 for the block F value. Now the P values is of course just the area in the tail. And notice we get that 0.04, and the next one should be 0.37. Yep, so that's the same. Now this next step I just think is so cool that I calculate the fitted values 3 different ways. M times Y. Remember the fitted values are Y hat. And then I M tau plus M beta minus J times Y. And then I just grab the fitted values from the model and I print them, column by column. And they're all the same. Residuals, it's I minus M times Y. And then I compare it with the residuals from the model statement that I had earlier, and they're the same. Now, part 4, estimability and contrast. I made up these 4 orthogonal contrasts. Now, contrast, they have to sum to 0, but orthogonal, if you dot product any of these two, it should be 0. Now, we want to calculate the sums of squares associated with each of these and test. So in the real world, you would pick meaningful contrast, that you want to compare this mean versus that mean, or this group versus this group, etc. I didn't do that. So this is just an illustrative purpose. Now P1 has a very specific order. P1 is associated with C1. And what I do is I take the first component, rep it B times, which is 3, and then divide by B, which it's always 0. And then 1, I rep it 3 times, divide by 3. Same way for all of those. And for this to be part of, or to be estimable, has to be part of the row space. And picking the P1, which in the previous videos, I called it row, but I have to use a P for this. So when we look at it, we take row times X, the design matrix, we get this, what I call a lambda parameter. And this is, this picks off, the first one picks off mu, the next 5 pick off the tau parameters, the next 3 pick off the beta parameters. But if we compare this section with our first contrast, they're the same. And they better be, because in order for this to be estimable, it has to be part of the row space. Now the sums of squares associated with the first contrast is this. I'm gonna just point you back to the video for this. Then what I do is I repeat the same process for the next 3 contrasts. So I create P2 based upon C2. And then I check to see if it's part of the row space, and this gets us the same matrix back. The sums of squares associated with it. P3, I'm going to go a little bit faster here. P4, P5, and the sums of squares associated with it. Now, I do want to point out that these orthogonal contrasts partition the sum of squares treatment, and that's what I want to show here. So if we add those sums of squares contrasts and look at the treatment sum of squares, they match 0.73244 exactly. And if we print out the ANOVA table, that's the sum of squares treatment. Now, let's explore the contrast a little more. So I just wanted to remind myself what the levels were. Now, E-means is a function, and it's actually library E-means, and this is supposed to emulate the least squares means in SAS, and I actually think it does a pretty good job. So I've put in the 4 contrasts, C1, C2, C3, C4, and I use the model mod that I used earlier. So then it comes up with estimates for our tau parameters, and then it calculates. Oh, let me make this wider and redo that. I want it all on the same line. So here they are. So this is the first contrast, the second, the fourth. And if we go back and look at the contrast values that we got, and I shouldn't do this. So this is the sum of squares contrast for 4.05. Then, yeah, I'll do that in a second. It's too confusing for me even. So, so let's look at the least squares of these contrasts. So first of all, I'll calculate the mean for each level. Now, here we're taking treatment 2 minus treatment 1. So if we take the mean of treatment 2 minus the mean of treatment 3, it should equal this, and it does, 0.31. Then we do the second contrast, and it is the same. So this is the average of treatment 2 and 3 versus treatment 4, and that's what this is doing. So it's taking the average of 2 and 3 and then adding it to 4, and we got the same thing as what the E-means function got. And then we can do the same, so minus 0.4 and then 0.12. Now here, let's see if I reprint them. So what the, actually let me just rerun that. And so what E-means is doing is, these are t-test statistics, t-ratios, but in my videos, these contrasts are chi-squared chi-squared random variables with 1 degree of freedom. So if you take the square root of a chi-squared with 1 degree of freedom, you actually get a t random variable. And so that's what I want to show you next, is if we take the square root of these chi-squared random variables, we should get what it has up here. So 1.16, that's the same. See, it rounded it right here. So that's a t-ratio, where in my videos, that is it's a chi-squared 1 degree of freedom divided by chi-squared with 8 degrees of freedom. And so that f with 1 numerator degrees of freedom square rooted is a t. And so then I just show you that they are the same. Now, I just took the square root. Actually, I used the principal root, but really the sign of that should match the sign of the estimate. I just were too lazy to put it in. So 2.34, 2.34, 1.89, 1.89. Now the p-values here, they calculated from a t distribution. I'm going to use an f distribution, the same, as my videos. So that's the same as this, right? P-value 1068, 1068, and the other p-values will be the same, even though I use an f and they use a t distribution. 0.03, 0.4, 0.03, 0.4, right? So it is the same. And now just one more little piece here. We're going to look at the mean of the ijth treatment. And so if we look at this lambda parameter, it picks off mu, tau 2, and beta 3. So I2, beta 3. And now we rep that, right? So we create a P, which then is, when we take it times X, we know it's part of the row space. So we get our lambda parameter back. And so this is our least squares estimate for the you know, second treatment and third block. That's our estimate for that, the mean response. And I do it two different ways. I just take the lambda times the least squares estimate of beta, or I take transpose rho times x. Now, to show you that it is indeed that, I calculate the mean in a different way. So we want the second level, which is potash 54. We want block 3. So we calculate the mean of the of 54. That's what this is. Then we calculate the mean of the third block. That's what this is. And then we subtract the grand mean. And notice we got the same thing, 0.04. And here, if you just want to do it by hand, you can take this minus, or that plus this, and then minus the grand mean. But refer to video 5 for that, or video 4. Okay, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.